One jet or 2,000 robots? The new math of warfare? Why every robotic mission makes the next one better. Modern warfare has always rewarded the side that adapts fastest. What happens when the machine starts adapting on its own? There is a concept in business that executives have been invoking for decades, ever since Jim Collins gave it a name in a book that sold 4 million copies and became the founding text of a certain kind of boardroom thinking. A flywheel, a system where each step feeds the next, where momentum, once established, compounds, where the breakthrough is not a single action but the architecture that makes every action more consequential than the last. It has taken a while, but that same logic has now arrived on the battlefield. Begin with a word that is easy to underestimate. Protection, not technology, not autonomy, not artificial intelligence, though all three will feature before this is done. Protection. That is the output that matters. Everything else exists to increase it, per euro, per unit, per deployment, per conflict. Understanding that hierarchy matters because it changes the question you ask at the start. The traditional defense industry asks, how capable can we make a single system? The answer, reliably, is very capable indeed, and extraordinarily expensive. High unit cost produces low volume. Low volume produces limited operational exposure. The system is tested, not lived. It gathers experience slowly because it is deployed sparingly, and deployed sparingly because it costs too much to risk. The loop being described here inverts that starting point entirely. Lower cost enables more deployments, not 10 units cautiously dispersed across carefully chosen theaters. Hundreds, eventually thousands. The system becomes present rather than precious, which sounds like a subtle distinction until you grasp what presence, at scale, actually generates. Data! Not data as a byproduct or a record-keeping exercise, data as the engine. Real terrain, real weather, real electromagnetic interference, real adversaries behaving in ways that no simulator, however sophisticated, fully anticipates. And, crucially, it is continuous. The system does not stop learning between procurement cycles. It learns on every mission. Consider what that looks like in practice. A ground robot deploys with a mechanized platoon escorting logistics vehicles through mixed terrain. During the mission, it encounters a combination of conditions it has not fully resolved before. Saturated forest ground, intermittent GPS denial, low visibility aerial threats threading through tree cover. It completes the mission, not perfectly, but successfully. The real work begins afterwards. Every sensor stream is captured. Optical, thermal, radar, event-based, the terrain profile, the navigation decisions, where the system hesitated, where it overcorrected, where detection lagged by half a second too long. That data is aggregated, labeled, and fed back in. Perception models are retrained to better identify drones through partial occlusion. Navigation improves its handling of soft ground under degraded positioning. Sensor fusion is recalibrated, then the update is distributed over the air, not to one unit, to every unit in the field. The next mission, whether in northern Sweden, Poland, or Ukraine, begins from a higher baseline. One robot encountered difficulty in a specific forest. Every other robot is now better prepared for every forest, not 10 robots learning 10 times, one robot learning once, and 1,000 improving immediately. This is where the logic diverges sharply from traditional defense procurement. A conventional system returns from deployment largely unchanged. Lessons are written up, perhaps integrated years later in a revised variant, a new procurement round, a fresh budget allocation. The institutional knowledge moves at the speed of bureaucracy. Here, learning is immediate, distributed, compounding. Better autonomy increases mission value. A system that perceives earlier, reacts faster, and coordinates more effectively does more with identical hardware. It protects more assets, reduces operator burden, expands what is achievable in contested environments. The same unit becomes more capable without becoming more expensive. Higher mission value, in turn, drives further orders. Defense procurement officers are not, in the end, buying robots. They are buying outcomes. If one system consistently delivers more protection per euro than its alternatives, rational procurement follows, not as optimism, but as arithmetic. More orders unlock manufacturing scale. And it is here that most defense models quietly break. Traditional systems remain semi-artisanal, low volume, long lead times, bespoke engineering that resists repetition. The alternative is an architecture built around commercial off-the-shelf components, modular design, and assembly logic closer to flat-pack furniture than to the great primes of the Cold War. Systems that can be built quickly in volume and adapted continuously. Scale drives down production cost. Supply chains stabilize. Component costs fall. Iteration cycles shrink. The cost curve bends. And lower cost per effect returns you to the beginning. More deployments, more data, more learning. The loop continues. Each pass through it strengthens every other part. Traditional defense optimizes for peak capability at low volume. Impressive on paper, limited in aggregate. This optimizes for cumulative capability at scale, systems that may be individually unremarkable but improve collectively every week. In a world where conflict is shaped by iteration speed, adaptation, and mass, the side that compounds faster holds the advantage, not because each unit is superior, but because the system improves faster than the adversary can respond. From platforms to loops, from procurement to compounding, from exquisite to scalable, and at the center of all of it still is that same word, protection.